Okay, with this, welcome everyone to this edition of our seminar series. I'm very happy to welcome so many of you here. I think we have a very interesting topic today and two very, very interesting speakers for that, talking about opening a new frontier for causality, which I think is quite exciting. And I will not talk too much about our presenters right now. I will leave that to Mihaela. What I want to point out before we start, though, is if you want to hear more about causality and a lot of more topics surrounding AI and machine learning, specifically for healthcare, the center will do a summer school in September, which is the first summer school exclusively for AI and machine learning in healthcare. We ran it last year already very successfully with over 450 people. I hope we are even more this year. We have a very exciting schedule, some very exciting speakers that we will start sharing with you in the coming weeks. If you want to find out more, please get to the website of the Center for AI and Medicine and have a look at all the information we have there on how to participate. And now I would like to hand over to Mihaela to introduce our two renowned speakers. Thank you.
Thank you very much, Andreas, and welcome everyone to our Cambridge Center for AI and Medicine seminar series. I'm really truly delighted to have today the opportunity to be the first group to hear about this fantastic research that Emre and Amit have done. And Emre Kiciman is a senior principal researcher at Microsoft Research in United States. And I will not go through his illustrious biography, but I'm going to say, as somebody that's very interested in causality and causal machine learning, I'm delighted that Emre is talking to us today because he's the co-founder of the DoWhy library for causal machine learning, which I'm sure many of you have heard about and use. Amit Sharma is a principal researcher in Microsoft Research India. He has also numerous awards, and I will also not go over his illustrious biography. I'm just going to say that he also has co-led the development of the open source DoWhy library for causal inference, as well as the DICE library for counterfactual explanations. And we were fortunate to have Amit talk to us almost a year ago when we talked about causality and causal deep learning. But at the time, large language models were not in the room. So we talked about more conventional ideas in causality. So it is wonderful to have him back today together with Emre, tell us about these new frontiers on causality in the era of large language models. Thank you very much, Emre and Amit.
So happy to be here. Thank you, Mihaela.
Thank you so much, Mihaela, for that introduction. So today, we are very excited to talk about how large language models may interact with causality. And some of the results we have found are so exciting that we believe that there might be a new frontier that it can open for causality. So this is joint work with Emre Kiciman, who will also be presenting today, Robert Ness, myself, and Zhenhao Tan. So the first question that may come to your minds is large language models and causality, right? If you're like me, I think even I was very skeptic in the beginning because all of us have learned that causality requires interventional data, right? So I was very sort of skeptic on what exactly can you even do, right? Does this question make sense or not? But over time, I think we have sort of investigated this and we found some impressive results. And so that's what we are trying to do in this talk today, just trying to unpack this question and then also lead you to some interesting sub-questions that we believe can help in moving forward. So let's first just take an example. Suppose you are a business owner and suppose you have some data of your sales. You have making toys and then you have a lot of sales in December, right? And you might suddenly think why that is. And as a user today, you can ask an LLM like GPT-4, right? So we might just type down their query. saying that this is a toy shop owner. They have a lot of sales in December. Plus, they also launched a new ad in December, right, compared to other months. So we can ask the LLM, was this causal, right? Was the ad that really made their revenue high? And you get some really impressive, surprising, shocking, depending on your state of mind, results, where GPT-4, for example, is able to give you something sensible. It does say you cannot just directly ascribe because there's a holiday season in December. And it also tells you to do an A/B test, right? So that's clearly good. And you start thinking that maybe there's something that language models are doing. But then let's say you just continue the query and you just give it another scenario where now we ask that in February, the toy shop owner now did some kind of an experiment. They showed the old ad in newspapers, they showed the new ad in online websites, right? And they did find benefits of the new ad. Now, is this causal, right? So what should the toy maker do in March? And so here GPT just runs along with you. Yeah, that makes sense. If you're getting more money, go ahead. It seems like the new online ad is more effective, right? And for those of us who know causal inference, we also know there's selection bias. And this example is a clear case of selection bias where there's a difference in population between the people who saw the old ad, newspaper, and the new ad, which were online, right? So I think we are showing you this example to make 2 points. One, it's a very hard question to answer on sort of whether LLMs can understand causal reasoning. We believe it's going to take much more work. But these examples are just sort of showing that there's something in here that needs study, right? And the second point is maybe that's not the most useful question to ask immediately, right? Maybe the most useful question to ask is whatever capabilities LLMs are exposing, how can we use them to supercharge causal research or to supercharge the causal practices that we do today? And so that's the tack we did in this paper. We are focusing squarely on, given the LLM capabilities that are available today, how can we use it to improve the state of the art for causal reasoning? So basically, domain knowledge is what we find that LLMs are really good at. And this is also kind of the Achilles heel of any causal analyst, because it's kind of the burden of a human analyst to provide this information, right? And what we are finding is that exactly the place where current causal methods are not good, which is providing domain knowledge, LLMs are able to do that. And we have coined a new term, which we are calling knowledge-based reasoning, which is to say that LLMs, rather than doing data-based or covariance-based reasoning, they're able to capture and provide the domain knowledge, right? So what we'll do today is that we'll showcase the knowledge-based reasoning of LLMs using causal discovery benchmarks. And then also capturing causal knowledge has implications for another branch of causality. It's on actual causality. And so we'll demonstrate benchmarks for that as well. And finally, I think we'll want to spend some time just thinking broadly on how this may open a new frontier for new research questions that we can all explore, and hopefully also enable the widespread use of causality. So let's dive in, right? We all are aware of different tasks, right? So as researchers, you might identify yourself working on graph discovery. You might think of yourself as a causal effect inference person, attribution, prediction, right? And so on. But as we started studying these topics, especially with respect to LLMs, we realized that causality is much broader than that, right? So even though, for example, we might be working on effect inference, how people look at causality is much broader, right? So let's just spend a second or two to just lay out that landscape so we also understand where exactly LLMs will fit in. So let's imagine our toy shop owner again. They have a real world task, right? How to improve my sales. Typically what happens is that people would sort of break down their real world task into specific questions. So some of these questions may be covariance based, which means they require data, right? This is, I think, often a lot of what we do in research. So they may ask, what is the effect of my new ad on monthly sales, right? And then you go ahead and do all kinds of statistical analysis, right? On the other hand, sometimes they may also ask, this particular customer came in and he did not buy anything, right? Why did this customer not buy, right? So these are more examples of logic-based causality, where you're really trying to think about the possible necessary or sufficient causes for a sale, for example, right? And at the same time, there are also a branch of causality which can be divided in terms of type or actual causality. So type causality broadly is just inference over a subpopulation. This is again, if you're doing effect inference, most of the times you're doing type causality. But there's also actual causality, which has relations to logic-based causality, where you're trying to only infer particular events, right? So for example, why did this customer not buy? I'm just mentioning these because I think this will help you contextualize where LLMs are fitting. And as you'll see, I think what they can do is really enable a substrate of services across all these tasks and help you combine them rather than thinking of them as separate tasks that you yourself have to combine. So can LLMs learn causal graphs? Yes. So promising results were already shown by Long et al. With 3-4 nodes. But there was also some sort of pushback on that by another set of authors, which showed that maybe it's true for 3-4 nodes, but for real data sets like a medical pain data set, we get very low accuracy using ChatGPT. But I think we have now sort of investigated thoroughly across many data sets, and we find that with the right prompts, yes, you can get good causal graphs using LLMs. Of course, they do it in a different way, but you can get higher accuracy also. Then the next question we'll tackle today is, can LLMs answer counterfactual queries and infer actual cause? So this one was interesting because today there's no existing method that can do that. So there's no existing method that goes directly from a counterfactual query in text and then gives you the necessary cause or gives you the root cause. Here, our answer is mixed. We find that not all LLMs are capable. So GPT-4 can, but for some reason, GPT 3.5 cannot. And so why it happens, what are the limits of GPT-4? Those are not well understood. And then finally, I think we already discussed this question, can LLMs do causal reasoning? I think this seems like the biggest question in the room. Past work has shown probably not. The great piece of work from Willig et al., where they called it that they're really just learning correlations of causal facts. But I think our answer is that this is too hard. For today, let's not aim for that question to be answered, but at least we'll give you interesting results for the first two questions. All right. So as I said, domain knowledge is critical to any causal analysis, right? So imagine that you're doing prediction, you're doing attribution, you might be doing effect inference. In all these cases, in a causal analysis, you start with certain assumptions, more often than not in form of a graph, right? So you create your graph based on some knowledge about how the causal processes are, and the entire process analysis after that is based on those graph assumptions, right? So based on that graph, you might identify using a backdoor criterion, you might estimate something, and finally validate as well. But the graph that you construct is really critical to drive your analysis. And before LLMs, there was a consensus actually among our community, but also among results in the literature, that using graph discovery algorithms was still not practical, right? So there were sobering results using SOTA discovery algorithms on real world data, not simulations. And that was because provably it's very hard to learn the causal relationships just from observational data. And so let's look at what LLMs can do, right? So I'll talk about two causal discovery tasks. One is the pairwise discovery task. So this has been a simplest of causal discovery tasks where I only give you two variables. Your goal is to tell me whether A causes B or B causes A, right? The second task we'll consider is a more harder task. And usually that's what people call causal discovery, where I just give you a set of variables and your job is to infer the full directed acyclic graph over them. So as you can see, this is a harder task. Not only do you have to infer the direction of the edge, you also have to infer which edges exist or not. But we'll go step by step. Let's take the easy task first. Let's take pairwise discovery. Let's just try to set up how exactly is it that LLMs matter here, right? How will you actually think about using LLMs for this task? And then once you use them, what kinds of results can you get? So you might be aware, I think a lot of you might have heard of this Tübingen benchmark. It's one of the celebrated, most common benchmark used for pairwise discovery. And we thought that if we had to test LLMs, let's just use that, right? Let's just see what happens, right? So when we started, we were not really sure. I mean, this is a very hard benchmark. So if you see even the current results being published today, existing algorithms achieve about 70 to 80% accuracy. Best is perhaps about 83%, right? And the reason is you can just look at the variety of the relationships here in terms of domains they come from. Some of them are from zoology, engineering, biology, atmospheric science, and so on, right? But of course, the methods that I'm talking about were just looking at the data. And for them, it was a hard problem just because of maybe the variance in the data that was recorded. So we thought, if it's such a hard problem, even theoretically, what would LLMs do, right? So our method was very simple, right? We said for each pair, let's input some prompts which have these variable names, and then record the output, right? If the LLM sort of records the right output, the right direction, then we score it as 1. If it outputs the wrong direction, then it's 0, right? It's as simple as that. So now the only question is, how do you prompt it, right? So the first thing we came up with was the simplest thing you can imagine. We just asked, does changing A cause a change in B? And vice versa, we can ask, right? And then we can just take the mean of these two answers. So one example could be, we ask, does changing the altitude cause a change in temperature? Please answer in a single word, yes or no. Right? And I'll show you examples of LLM's outputs. But this is just to show you the methodology of how we were thinking about this. But then as we progressed, we started becoming slightly more nuanced in how we ask the LLM. So we were looking at recent literature that how you ask, what kinds of ways in which you prompt the LLM really matters. So then we came up with some different prompts. I'll show one of them, which we chose at the end, which we call the single prompt. So first, it sort of combines both these questions because we hope it can give more information if you're comparing both options at the same time. So now we're just asking which cause-effect relationship is more likely. And then we also use some work in LLMs on chain of thought reasoning, which asks the LLM to work out something in a step-by-step way. And it has the nice side effect that you can also see the LLM's reasoning, so-called, right? So you can see the output that justifies the LLM's answer. And so now you can ask the same question, but now you can ask it in a simple sort of a single question. And we are looking for an answer from the LLM, which is either A causes B or B causes A. Here's an example. I think throughout this project, we had many such cases where one time GPT-4 or GPT 3.5 would just amaze us, and the next time it'll just disappoint us, right? And so this is one of those examples as well. So we ask relatively simple question like, does changing the age of an abalone is an organism, cause a change in its length? So the first time the GPT answers pretty reasonably. It says, I have some biological knowledge, and so it's likely that changing the age should matter, right? That's the relationship. But then we ask a very simple question, very similar question, which is now changing the age of an abalone. Does it cause a change in its diameter, right? And length and diameter are almost the same if you're actually reasoning causally, right? But here the LLM sort of just falters, right? The same exact model, when asked a question with a slightly changed input, it gives the wrong answer, right? So now it thinks that the diameter is what causes the age of an abalone. And so this example would sort of make you think that, what? I mean, this doesn't make sense, right? I mean, how often are you just going to keep asking? But I think what the truth is, and what we found in our results, is that these kinds of errors are very rare. For whatever reason, maybe it's a large training, maybe it's the amount of data that's been fed into these models. The number of times such errors are made are surprisingly small, right? So as we sort of, rather than just manually doing these comparisons, when we started compiling the results, we were shocked actually at the accuracy that these models were getting. So let me walk you through the results and also put you into context the other results that were coming from covariance-based research. So the table that I'm showing you here has accuracy and weighted accuracy. Weighted accuracy is just an unbiased way of measuring it, so you can just ignore that for the moment. So there were many algorithms before language models, which are covariance-based. They're looking at the data. And as you can see, the best accuracy was about 83%. When we tried out our 2 prompts template, we first saw that smaller models don't work, right? So if you see models from OpenAI like Ada, Babbage, or Curie, they are as good as a random guess, right? 50%. What we start seeing interesting patterns is with increased model size and perhaps also RLHF, are models like Text DaVinci, where with the 3rd generation, which is essentially GPT-3, you're able to get about 82% accuracy on this task, right? And again, we are not providing any more information about these variables except the names of these variables, right? So this was pretty encouraging. So now we sort of thought, okay, maybe there is something more, right? So we looked at this simple change where you can change a system prompt. So a system prompt is a so-called thing in chat-based LLMs where you can just sort of prompt it to be in a certain part of its probability space, right? So here, for example, we just add that you are a helpful assistant for causal reasoning. Pretty inane, simple sentence, right? And this actually gives us a 5-point gain. So if you look at the results, the bottommost row here, GPT 3.5 Turbo, this is ChatGPT, with a causal agent now gets us up to 86%, right? That was exciting. And then we got GPT-4 access. So we thought, great, if we have GPT-4 access, we should try it as well. And just out of the box, we changed nothing. We kept everything the same. GPT-4 gave us about 97% accuracy. And so I think 2 comments are in order, right? 1, there's definitely something happening here. And 2, we don't know what that is, right? So I think what we'll try to do now is to just try to see how much of it is transferable. And also later we'll try to see how much of it is maybe just due to memorization, right? But yeah, I think there is definitely something. Now we want to understand better how the heck is this working. And just a side comment, I think these are not comparable algorithms. So the first set of algorithms are using data, and what we are presenting using LLMs are using knowledge, or essentially domain knowledge. But the interesting part is that maybe in a future we can combine them and have more accurate algorithms. We also found some interesting insights, which I think would be useful as we move towards a more LLM-based world, where, for example, there's a pair in this data set, which is ozone concentration and radiation. If you just ask GPT-3, what is the relationship, it would actually tell you that decrease ozone concentration causes radiation, right? And our benchmark would say, no, that's wrong. And we thought GPT-3 is getting most of these right. And this kind of makes sense because you can read this, right? And so what's wrong? What we realized was that the benchmark was constructed for ozone concentration at the ground level, whereas this answer was based on ozone concentration in the stratosphere, right? And so both are correct, right? And so what we tried was then let's just prompt the LLM again and ask it that we are specifically talking about ozone at ground level, right? And not the stratospheric ozone. And once we do that, we do get the right answer. So just showing this example to say that when you're prompting LLMs, being specific really matters. And so part of perhaps the work now is to, given a data set or given a new problem, thinking about how you're naming your variables or how you're providing your metadata. So we wanted to see now how general it is, right? General in terms of more data sets, but also general in terms of more domains, right? Maybe it's easy because Tübingen was a popular data set, but what if we try some really new data sets or data sets which are not available on the web as easily, right? So that's what we did. So we tried on a data set called the neuropathic pain data set. This has been collected by Tu et al. In collaboration with medical doctors, right? So this is about 221 nodes and 475 edges. And if you just see the pairs in this data set, you will realize that this is different, right? So this is something very expert driven, where a normal layperson may not be able to make sense of these variables. And so we thought this is a good test, right? Just a good test of a very specialized knowledge and checking whether the LLM can also transform that knowledge from its training data or from its world knowledge and give us the causal relationships. So for example, I had no idea. I had to search. I learned a lot actually in this project, searching for DLS, Oracle, and so on, and what they mean. But we found similar results, right? So with sort of the same prompt that I showed you earlier, very little changes, a similar pattern emerges. Smaller models can't do anything. GPT-3 and GPT-4 models are good, and they can get us up to about 84% in just predicting the direction of the edges, right? So remember, what we are doing now is just pairwise discovery. So for each edge in this large graph, we just ask the right direction. And then finally, when we tried GPT-4, it was again able to give us accuracy in high 90s, 96%. And sometimes there are incorrect answers, of course, right? And as I've also shown you with an example, some of these incorrect answers are just nonsense, right? So at no point we are claiming that LLMs have sort of solved this problem. They have many errors, but also sometimes these errors are also interesting. They can help you question the benchmark itself, or at least help you correct or improve your benchmark thinking. So here's an example which took us some time to decipher, right? So there's a condition called L5 radiculopathy, which is essentially pain in your lower back. And there's something called obesity, which I think is a more common term. And so the benchmark says correctly that L5 radiculopathy can cause obesity. The LLM output did not agree. It said obesity causes L5 radiculopathy. And reading the answer, it kind of made sense. So we checked the medical literature. And it turns out that maybe in some world, we are not medical experts, but it seems from the medical literature that obesity is also a risk factor for radiculopathy. And so this was another interesting use case of how LLMs are not just for discovering or comparing on a particular benchmark. They may also help domain experts create new benchmarks, right? It's a tedious task to label 475 edges, right? And so they can help you do this task as well. So now let's move to the real causal discovery, right? Those of you who might work in causal discovery would say that's easy. Like, pairwise is fine. Discover the full graph, right? Then I'll see. So let's try that. So we thought, okay, fine. I mean, it's working well. Let's give it a shot. And here we did kind of a very naive thing. I expect if you are experts in this topic, you can do something much better. So what we did was we completely ignored the acyclicity, right? We completely ignored the fact that you have to discover the full graph. We just said, let's just repeat our pairwise experiment and let's just do it on the entire set of nodes that you have, right? So completely sort of a brute force way of putting the pairwise algorithm into full graph discovery. So for the neuropathic pain dataset, we were using this 100-pair subsample, again from the dataset authors, Tu et al. And this was nice because I think it's a small dataset, so it's easier to compare. And we had results from Tu et al. Already on this dataset. So it has 50 correct edges. It has 50 incorrect edges. And so now the task is threefold, right? Whether A causes B, B causes A, or nothing. Like there's no edge at all. So that's our task. We slightly change our prompt. There's a third relationship also now. No causal relationship exists. And so what we found was here, the prompt really matters. So if you think about this task with random, you can get about an F1 of 0.33. With Tu et al.'s previous results, they tried ChatGPT, but they tried a really simple prompt. I think similar to our prompt earlier, does A cause B, right? And in that case, their F1 was about 0.21. With our improvised prompt, what we found was that the F1 can be increased significantly. And the F1 that we finally got with GPT 3.5 was about 0.68. So if you see the relative increase, it's about 3 times. And that sort of just tells you that it's not just the LLM, right? It's not just whether you have GPT-3 or GPT-4 or GPT-5 if it comes. I think it's also a matter of how you combine the LLM with a prompt that helps you on your task. And so in our specific task of causal discovery, we believe we have now a relatively stable prompt that you can use for any new data set. But we also believe there'll be more improvements to it that can make LLMs might even more better for these tasks. And then again, a final data set we tried just for diversity was on atmospheric science, right? So moving from medical science to atmospheric science, maybe that's less well discussed on the internet. It's still a more niche topic that some researchers talk about. And so we found this Arctic sea ice data set where researchers had already compared SOTA deep learning discovery algorithms. It's also nice that it's a small data set, so it's only 12 variable network. So we could actually run GPT-3 and GPT-4 on the entire graph, right? So now we can discover the entire graph and compare our results. So the variables, again, I think won't make sense to us, or at least, and many of you, like things like geopotential height, meridional wind, short wave, long wave flux, etc. Right? So what we find is that TCDF, no-tiers, and DAG-GNN, all sort of great methods from the covariance-based literature, obtain about a similar Hamming distance. And so here NHD is Hamming distance, smaller is better. It's a distance of the graph that the algorithm discovers compared to the true graph. So GPT 3.5 as well just gets similar Hamming distance. It's about 0.33. But GPT-4 actually can get 0.22 Hamming distance, which is again like a 2/3 difference. Sorry, 1/3 difference. And that's again significant. We didn't do much more analysis here because our goal was just to sort of show the potential. But I think in the future, we can imagine more advanced techniques that can first sort of help us discover graphs using LLMs that reduce NHD even further. But then also more interestingly, combine it with no-tiers or combine it with some covariance-based algorithms to make it even better. So with that, I would like to pass it on to my colleague, Emre, who's going to take a more sort of a cynical view and sort of think about whether it's really what we're measuring, whether we think what we're measuring is really what we're measuring.
Thanks very much. And I think the animations on this slide are broken. Can you advance a couple steps on it? Yeah. Great. Yeah, so we've seen really, I think, impressive results of using GPT-4 to draw out a causal graph for a particular situation. And this is really exciting as a source of domain knowledge. But we have to ask ourselves, what really are we testing, right? We are asking a question, and we need to know whether we really believe that GPT is answering the question as an evaluation of what we think we're evaluating. This is a challenge in benchmark-based evaluation of large language models generally. If the large language model has been trained on the questions and answers for a particular test, whether this is a medical exam or legal exam or elementary school, middle school, upper school, tests of math and reasoning, etc. The threat to the validity of our understanding of the benchmark is that rather than actually performing the task we're asking it to perform, the large language model is simply repeating back the answer that it's memorized in the past. So we want to understand whether that might be a threat to the validity of our benchmarks that we showed here. Now, there is some nuance. When we're asking the large language model to repeat back causal knowledge, whether A causes B or vice versa, we are actually, in some sense, assuming that the underlying knowledge is memorized, right? We hope that it has learned something from all of the text that was used in its training data set. And so this is going to mean something a little bit different for us. But let's first see whether the data sets we're looking at are memorized or not. And the way we're going to do this is going to be by looking at the raw data, the source data set for that is out on the internet, and we're going to ask the large language model, rather than asking it to think about the implications of the data it's seeing for a causal mechanism. We're just going to go down to the raw low-level data and ask the large language model to repeat back the raw data itself. So we're going to start by telling the large language model in this experiment that it's an AI assistant that is built to memorize data. And we're going to point it at the README for the data set. We're going to give it as much context as we can. And then we're going to say that we're going to test its memory by putting in a prefix, the first couple of columns from one row of the data set. And we want it to repeat, complete that row and give us back the original data. And so this, for example, looks like here the user now types in the first two columns of the Tübingen data set, which happen to be a pair ID, a row ID number, and then the first column is one of the elements in the causal relationship that this row is capturing. And we say, what is pair 5 and age? What's the rest of the row? And GPT correctly completes the rest of that row by saying the rest of the columns are length, abalone, and then the directional arrow. And if we repeat this across all the rows, we see that the GPT models 3, 5, and 4 are able to correctly complete 20% and 25% of the rows without error, respectively. If we look at individual cells that are being completed correctly, that number is much higher, gets about 60% of the missing cells correctly. So clearly, the Tübingen data set is in the training data set, and a large chunk of this information has been memorized. What does this mean for our understanding of the benchmark? Next slide. So we have to think what this means for what we're measuring out of this benchmark test. So to understand this better, we think about what we believe the large language model might be doing. What is this knowledge-based discovery task we're asking it to do? And we're going to separate this out into two parts. One is the probability of D, the likelihood that this knowledge that we're asking about at its core is already known by the large language model. The second part is going to be, given that the large language model knows this information, can it transform it to answer a particular question in a particular context? So now this is P of D is the likelihood that the knowledge D is known, and then P of Y given D is the likelihood that the LLM is able to use that knowledge to answer a question correctly. And so knowing that the Tübingen data set has been memorized, has been seen in the training data set and largely memorized, then we know that our benchmark is not measuring P of D. That is just given that condition is satisfied when we look at the Tübingen data. What we are measuring then, when we look at that 96% number in the pairwise causal discovery benchmarks, what we are measuring is how the LLM can process and transform D into that necessary causal relationship that we're asking it to give us. So there is some transformation. What do we mean by that? It means that it has to recognize that we're asking about causality. It has to look at that tabular data format where we were, had that's in the raw data file, and transform that into the English language response to our question or the multiple choice response to our question. And so when we talk about the results here, that's really what we're doing. So I think one of the questions in the chat was, what are the odds that the large language model gives the wrong causal response because it's learned the wrong causal response from the training data set? That is not being measured by these benchmarks because that is captured in this P of D. What is the likelihood that the correct knowledge D is already known by the large language model? So that's a really interesting question, very important question, obviously, but these benchmarks don't capture that because the data has already been seen. It's worth noting that we're only able to run this memorization test as presented for the Tübingen data set because that's the one that's available in a text-based tabular format that's amenable to this type of row completion task. The neuropathic pain data set is available in a graph-based format, like in a JSON graph representation, and the Arctic sea ice also is not available in a text-based format. And so those are data sets that we were not able to where we were not able to look at whether the underlying data is memorized, but are good representations, again, of this type of process of transforming the underlying knowledge into this natural language representation, which we're asking. We also wanted to better understand what might the large language model be paying attention to when it answers the questions that we're asking. So we ask which cause and effect relationship is more likely, give multiple choice answers, and ask the large language model to work things out step by step and give us a final answer, in a clearly formatted tag format. What we did to understand this was to repeat each of these questions, but to redact each word one by one. So we would randomly pick one of the words in this question, and we would replace it with a redaction, X's, and we have X's is what I'm showing here. And ideally, Xing out a word is only going to affect the final answer if we're Xing out an important word that changes the underlying meaning of the question. So, for example, the word changing is the most important word here in this experiment. That means that if we remove the word changing, the LLM is more likely to give us the wrong answer or to misunderstand the question for some reason. Similarly, the tag format at the end that tells the large language model how to respond, that is also very, very important. It will not give us the answer in the right format if we remove that. And so these types of important words that are critical for the instructions that we're giving it, we expect those and hope that those will affect the result. The ones that we're more concerned about are maybe some of the words like the, or some of the smaller like preposition words where you would expect a human would be able to correctly answer the question, even if there was a typo or something that caused that word to be missing. But we do see that most of the words that are darker are actually the more important words. And so that gives us some confidence that it's doing the right thing, but this does need greater study to help us understand what really is the large language model paying attention to, so that we are able to both improve the underlying prompt and also have more confidence that it's giving the right answer. So the takeaways from this causal discovery section are that we do see large language models enabling knowledge-based causal discovery. This is not the same task as data-based or covariance-based causal discovery. We think it's a complementary task that's able to draw out the edges between graphs. But we do see that the performance, just as a benchmark, does give competitive performance in determining pairwise causal relationships across multiple data sets in different domains. When we adapt this task to provide full graph discovery, we do see that there are additional challenges because this task now brings in concepts that are a little more complicated, like distinguishing between direct and indirect causes. But we still are finding that the large language models are providing non-trivial utility. We think that this is at a minimum useful as a bootstrap to help analysts get started with a causal graph. Might be also useful as a critique when an analyst comes in with their own causal graph. And potentially as the methods improve, as the models improve, and as our prompting methods improve, we think that we could take this much further as a more dependable source of full graphical knowledge. When we look at carefully at the construct validity, it is worth emphasizing that our results are valid measurements of the large language model's ability to transform knowledge into an answer, but that we do have to be careful to understand that we are not testing with these tests the likelihood that any particular causal fact has been memorized. That will take a bit more work to identify a way of getting knowledge that hasn't been included in the training data set, that could not have been included in the training data set for GPT. Yeah. So part 2. So as we talked about at the beginning of the slide, at the beginning of the deck, as Amit mentioned, there are many different kinds of causality, different tools that are being used by causal practitioners and researchers in different subfields across academia to solve the different kinds of problems that people want to apply causality to. So we wanted to take a look at not just the covariance-based tasks, causal effect inference, etc., that many people look at. We also wanted to take a look at some of the tasks that that might be still quite difficult for us to automate to date. So we're looking at actual causality in this section, and I wanted to give you a couple of examples of what is an actual causality task. So whereas type causality is inferring making an inference over a subpopulation and talking about average effects, for example, actual causality is really focused on a single event and asking about what caused an outcome that we've seen in this specific scenario. So for example, whereas type causality might be asking whether smoking causes lung cancer in general, actual causality is focused on a question that's more like, Bob has lung cancer and smokes. Did Bob's smoking cause his cancer? Or like our shopping example, rather than asking whether a customer who sees a newspaper ad is more likely to buy a toy on average, the question in an actual causality setting might be to say, here's a specific customer who did see a newspaper ad and then came in and bought some toys. What would have happened if they hadn't seen the ad? This is a very specific counterfactual question in this actual causality setting. Similarly, a similar counterfactual question would be, a doctor washes their hands before surgery. What would have happened if the doctor hadn't washed their hands? One of the challenges of, next slide. Thanks, Amit. One of the challenges of addressing these types of actual causality questions and addressing them automatically is due to the difficulty of formalizing a lot of the causal context that's necessary to answer these questions. So whereas when we're looking at data, we are able to, we have gone ahead and built automated algorithms to analyze data for us, these statistical estimation methods. It's because we believe that once we've gotten past the setup of the causal problem, there's still a lot of hard work that needs algorithmic support. In the actual causality setting, we believe that much of the really hard work is actually involved in the initial setting up of the causal context. So identifying what factors are relevant to the causal question, thinking about what are the relationships here, are causes that we're seeing necessary or sufficient, and then considering for a lot of these causal tasks, we also end up, if we're trying to replicate the way people think about these causal questions, we also have to start thinking about normality, morality questions, intention, in order to match up with how humans reason about causality, attribution, blame, etc. And these tasks are actually some of the reasoning through these tasks take a long time. This is like the heart of an actual causality problem. So it's really exciting that we might be able to make some progress on this front. And for our first test, we're going to look at whether a large language model is able to solve one fundamental building block of actual causality, a counterfactual reasoning from text. And this is counterfactual reasoning is a key element of actual causality. It's often how we, as people, reason through an actual causality question. We start to think in our head what would have happened, or we start to mentally simulate alternate outcomes. And in one of the formal definitions of actual causality, counterfactual dependence is built exactly on counterfactual reasoning. It's also useful when we are in decision-making and planning scenarios. So counterfactual reasoning is actually a broadly useful foundational skill. So our takeaways on actual causality, I encourage you to read the paper for more details on these, is that we do find that large language models are able to achieve new benchmark accuracies on counterfactual reasoning, 92% accuracy for GPT-4, not as good for the other models, but this is starting to now approach human baselines. We find that GPT-4 is able to understand scenarios and extract out necessity and sufficiency from text and understand background context. For example, in the hand washing scenario, if you ask what'll happen if the doctor doesn't wash their hands, the LLM is able to pull out that an infection is an issue, even though infections weren't mentioned in the original text. This is something that was not possible before. Even though we're not getting as great, 90+% accuracies with GPT-4, this is really starting to give us something we think that is qualitatively different than what we could achieve in the past. And now we think that these types of results, both the causal discovery results and these actual causality results, next slide, are opening up a new frontier with causality. And so we want to tell you what we see as being new with causality now with large language models. Primarily, large language models are providing domain knowledge that wasn't available programmatically to us before. We had to ask a human expert, and that was a significant burden on practitioners. This is where a lot of people have problems when they're trying to run a new causal analysis. We can ask the LLM for this information explicitly, and we also see that it is able to be implicitly pulled out in background knowledge for analyses as well. The large language model also gives us a flexible natural language interaction method that can help us augment existing tools, for example, mapping domain questions potentially into causal questions underlying, into the causal formalization of those questions. And the ability of large language models to extract out key primitives of actual causality, like necessity and sufficiency and normality, etc., opens up the possibility of building systems that can analyze actual causality in practice. This is something that wasn't feasible before because a human had to sit down for potentially hours and think through these things and do all the hard work before you could think about automating the logical reasoning. Now, this doesn't mean that everything is changing with large language models. In particular, we think that we still need rigorous, well-documented, verifiable analyses, especially when we're talking about a high-risk and a high-value task, like evaluating whether a vaccine works, whether medicine works, for example, whether an economic policy is the right one to take. We have to ensure that our causal reasoning is correct for these types of critical decision-making scenarios. And so we think that this is not something that's going away. We can't just trust the large language models. We need to do more work to make sure that these analyses are correct, even when done by a machine. In practice, we think that there are some earlier, lower hanging fruit that we can go after to have implications for practitioners. We think that augmenting human expertise with large language models, immediately bringing in this domain knowledge to assist practitioners in graph creation and validation, and enabling easier use of the end-to-end causal tools is the first place where we can bring these large language models in to support practitioners. And from a research perspective, we think there are many new research questions as well. So we've focused on knowledge-based causal discovery, but we believe we're only scratching the surface here. We think that there's many questions about what are the best way to combine knowledge-based and covariance-based analyses. Do we need to be doing knowledge-based analysis first, to drive the priors for covariance-based analysis, or should we be doing the covariance-based analysis first and then asking the knowledge-based approach to fill in the details when there's ambiguities in the data that we're seeing? I'll skip through. I'll skip through the rest of these research questions and perhaps leave them for the discussion. So I think to summarize the takeaways that we hope that you see in this work is really that LLMs are able to mimic the capability of extracting out domain knowledge that heretofore was really a burden on the human analyst. This enables a lot of new approaches to causal analysis, both in the covariance-based analysis and in the logic-based reasoning that we've been seeing. We think the main implication of this for practice is going to be to reduce the burden on the human domain expert. And if I had to pick out one research question that I'm most excited about, it's about a potential new ability to combine logical and covariance-based analyses more fluidly. If we have this glue of domain knowledge that enables us to automate both sides of logical and database analyses, then I think we can in very interesting ways go back and forth between these different forms of analysis to open up new kinds of approaches to validation, to asking causal questions and answering them based on the evidence that's at hand. I'm really excited that you were able to join us for this talk, and we look forward to continuing the discussion both now and in the future over email and as a community.
That's fantastic, Amit and Emre. Thank you so much for this fantastic presentation. And because I'm a human and not ChatGPT, I'm going to contradict myself, and I'm going to take the advantage of the fact that I have invited you to give this seminar to put the first question. And I'm going to ask you, Emre, to go back one slide and tell us exactly about what you think is going to be interesting, especially since the two of you are now really have evaluated so well the power of prompting, if you like. I would be quite keen that you go through other things, especially point 4 of how you see human and machine collaborating on this, and more generally. So maybe I will contradict myself, and even though some people may need to drop out, I think the topic is so important that we should hear from you, who are pioneers in this field, your thinking about the next research questions, and then we will take them from the chat.
Okay. So you mentioned the human large language model collaboration. I think there's a question about what is the interaction paradigm that for the human to work with the large language model. I think of this in a couple of different ways. Perhaps one is who's in the outer control loop, who's in the next inner control loop. Is the human strongly involved in every individual step of the causal analysis process, or is it more of or is the human more of a supervisor? One of the things that struck me when as I've been reading some of the books out there and papers where people are applying, for example, large language models to ask and answer medical questions, is how many of the questions that they're asking are causal questions. So here's someone's medical record. Please diagnose the illness for me, and why do you believe that? What are the symptoms that you're seeing that make you think that it's not this other disease? What if we ran another test and the result comes back like this? Then would that change your diagnosis, etc.? Now, these are all causal questions. What struck me is that they're not necessarily easy to map directly to the kind of very the kind of common ways that we think of causal tasks. So is this an effect inference question? Is this a attribution question? We have these boxes that we use for developing causal analysis methods that we've kind of standardized. And looking through the ways that people interact with GPT in these scenarios, their questions are causal, but they don't easily fit these boxes. And so I think that's one of the things that I'm most excited about, is this opportunity that we can now express those causal questions. We have a machine that can understand those causal questions. Now the question is, can we go down a level and make sure that that causal question is correctly framed logically and grounded in data to answer these new forms of questions that we haven't been thinking about in the past.
Yeah.
Fantastic. Thank you so much. Sorry, Amit.
Yeah, let me just add quickly, I think 2 points, right? So one is, as Emre mentioned, there's this human LLM collaboration. I think we're also thinking of the LLM and causal algorithms collaboration, because the human LLMs might be talking in natural language. We need the LLMs to convert that into either a causal question, like in DoWhy, or maybe even a logical sort of statement that you can later analyze, right? So I think that's sort of an interesting direction where we might see more work. The other thing that I'm very excited about is point 2. We didn't do this in this paper, but I think there are clear signs that you can just do this now for the kinds of causal inference that's done in epidemiology or economics, right? You need to find instrumental variables. You need to find negative controls. If you're doing studies, you want to think of what variable can I find that if I just sort of use that, then I can control for it and check whether my estimate is correct or not. So I think those kinds of questions, again, were sort of very hard and were left to best researchers. But LLMs can at least help you sort of guide and give you suggestions and give you different kinds of answers, right? So I think that's where I feel like the immediate part will start, where the best researchers will start using them as assistants. But I think over time, we may be able to hopefully make them robust so that you can even sort of think of them as algorithms in the future.
Fantastic. Thank you so much. There are many questions. I'm going to start with Jean-Baptiste because I see a lot of questions from him. So Jean-Baptiste, if you don't mind, maybe you come online, and maybe Amit and Emre, you stop sharing. And
Okay.
Jean-Baptiste, maybe you can group some of these questions such that I saw that some of the questions have already been answered, but I don't know whether all of them have been answered. I'm going to ask you a question from Chinyuan who needed to drop out, but I think his questions are pertinent, so I'm going to ask them and others can hear your answer. So first was, why can the question, why did this customer not buy from my store, be solved by logical reasoning? And does logic mean deduction here? And he says, I can't see we can get an answer to that question without uncertainty. So that's the first question from Chinyuan.
So I think we do see that the large language models are able to, in some of our point analyses, we can ask the large language model whether, what would change its mind, what it's uncertain about, and it will give us an answer. So there's something potentially going on there. However, it's difficult to know whether the large language model is giving us a post hoc justification. Is it generating uncertainty because we ask whether it's uncertain, and so therefore the most probabilistically correct answer is to say yes, I'm uncertain for some reasons. But as an example of the ozone and radiation example that Amit stepped through earlier in the talk, where the large language model is giving the wrong answer because it's thinking about ozone and radiation in the stratosphere instead of a ground level. After you ask that question, you can ask it, and what is there any ambiguity? What would make you change your answer? And then that is sufficient for it to say, well, there's this other kind of ozone, that's at ground level, and this other kind of radiation, not UV radiation, but radon. And if that's what you're asking about, that would change my answer. So it's really interesting that we can start to see this, but it'll take more rigorous analysis and experimentation to explore the limits of that.
Fantastic, thank you so much. I don't know, Jean-Baptiste, are you now able to unmute yourself and ask your question? If not, I will ask it, and then I want to ask anyone else if there are who is here to maybe come on camera and ask their question. I think Andrea's question was answered already, but so I'm asking the question of Jean-Baptiste, with the causality ability you explain, then I feel that adding background information or rules or do's and don'ts will help the text generation. From your experience, what are some better ways to encode rules to the large language models?
Yeah, so there I think we found this general template that seems to work, not just for causality, but for other tasks as well, where you can think of your whole prompt itself as composed of 4 or 5 pieces. The first is sort of just describing the task and setting up the context for the LLM. So for example, you are a helpful assistant to a toy shop owner, and here's your task, right? The second is the list of rules, which kind of add more nuance to that task, because for this particular shop owner, you might have some rules in the country and so on. And so what we found is that really sort of a listed rules, like 1, 2, 3, 4 bulleted list of rules works well. And then later you want to give some examples, like maybe some few short examples, and then finally a question that you really want to ask. The reason this sort of simple structure works really well is that you can now mix and match your rules. So if you have some automation, you can sort of try different subsets of rules, you can add and delete rules and so on. And very quickly you can find a reasonable set that gets the LLM to what you are getting it to ask. The other quick thing I'll add is a very interesting paper, which I'll suggest people read, is called Automated Prompt Engineer, APE, where they completely flip the questions. They say you don't need to write the rules. What you do is you just give some input-output demonstrations to the LLM. So you might say, here's my problem, and here's the input and output that was generated. And the question you ask the LLM is, can you guess what the task was? Please write me a short description for the task. And in our experience, it sort of works really well. In fact, for the actual causality section, we did use that to generate some of our prompts.
Very, very interesting. I think we can stay for a very long time and ask you questions. So given the fact that usually the seminars are 1 hour, but I think that this has been so amazingly interesting that we are justified to run over time. I'm sure there are many questions to you, but probably we will ask everyone involved to write you an email. Thank you very much, Amit and Emre, for presenting this just hot from the from your writing. I should have asked you as a very end question, did you use ChatGPT in improving the quality of your paper that you have archived?
I think the one place where I used ChatGPT was to generate the too long, don't read summary sections, at least the first draft of them. And then we went through and edited, of course, to make sure it captured what we wanted. But it was an interesting exercise to see what it pulled out as the highlights of each section.
Fantastic. Thank you very much, both. Thank you very, very much. And we look forward to see new papers from you coming as this area is developing. Thank you again.
Thank you for inviting us.
Thank you so
Great
much.
to be here.